Hello and welcome to the Data Engineering Podcast, the show about modern data management. When you're ready to build your next pipeline or want to test out the projects you hear about on the show, you'll need somewhere to deploy it, so check out our friends over at Linode. With 200 gigabit private networking, scalable shared block storage, and a 40 gigabit public network, you've got everything you need to run a fast, reliable, and bulletproof data platform. If you need global distribution, they've got that covered too, with worldwide data centers, including new ones in Toronto and Mumbai. And for your machine learning workloads, they just announced dedicated CPU instances, and they've got GPU instances as well. Go to dataengineeringpodcast.com/Linode, that's Linode today to get a $20 credit and launch a new server in under a minute. And don't forget to thank them for their continued support of this show. And you listen to this show to learn and stay up to date with what's happening in databases, streaming platforms, big data, and everything else you need to know about modern data management. For even more opportunities to meet, listen, and learn from your peers, you don't want to miss out on this year's conference season. We have partnered with organizations such as O'Reilly Media, Corinium Global Intelligence, ODSC, and Data Council. Upcoming events include the Software Architecture Conference, the Strata Data Conference, and PyCon US. Go to dataengineeringpodcast.com/conferences to learn more about these and other events, and to take advantage of our partner discounts to save money when you register today. Your host is Tobias Macy, and today I'm interviewing Frank McSherry about Materialize, an engine for maintaining materialized views on incrementally updated data from change data captures. So, Frank, can you start by introducing yourself?
Sure. I'm Frank McSherry. I'm Chief Scientist at Materialize Incorporated. I used to be, I would say, much more of an academic. Did a lot of science research, computer systems, data processing. Things go back 15, 20 years or so a bit all over the place. I did a bit of work with differential privacy back when that was just beginning, and that, just a lot of things related to data processing, big data processing, mostly understanding a bit about how computations move data around at large scale and what they need to do this efficiently, what sort of support they need. And
do you remember how you first got involved in the area of data management?
Yeah, I mean, it goes back a ways. So as a grad student doing computer science-y whatnots, I was a theoretician originally, so proving theorems and doing math and stuff like that. And the work that I did related to large graph analysis, basically. So trying to understand, back at the time, this was like 2000 or so, PageRank was just barely a thing, and people were pulling out other sorts of analyses about what do you do with really large graphs, the web at the time, but other sorts of social graphs, things that have emerged out of people's interactions rather than being planned ahead of time, like a network topology. And this led to a bunch of, practical questions about how do you actually, so someone gave you a billion edges, what would you do with that? How do you even make that work? And at the time, I was at Microsoft Research, but at the time, people like Microsoft and Google and potentially a few other places, Alta Vista type places, were the ones working at this scale, and it was very bespoke technology that people were using. And as part of wanting to work with these sorts of problems, got involved in projects, in particular at Microsoft with the Dryad project, the Dryad Link project, which are sort of these cool DSL in C# languages that trick people into writing declarative programs in a way that you see now in Spark and stuff like that. It's work that sort of, I think, drew a fair bit from Dryad Link. But it caused me for sure to realize that a lot of the programming idioms that we use to work with large data really rendered down pretty nicely to data parallel compute patterns that you might ask a computer to perform if you could manually control where all the bits and bytes go. But through an interface, through an API that was much more pleasant, a bit more declarative, and was sort of lifting the abstractions up to something that looked, I wouldn't say like SQL, but a bit more of a, let me just explain what I want to be true about the output rather than exactly how I need to go into it. And that project burbled around for a little while, did a lot of really cool things. And from my point of view, led to the Naiad project, which was the next thing that I did there. And that was sort of where I got a bit more directly involved in building systems for data manipulation, data management, data. To be honest, a lot of computation. Like a lot of what I do, I would say, is more about computing on data rather than managing it per se. Or at least other people work a lot harder on data management than I do. There's a lot of talking. Hopefully that gives some context as to the past, let's say, 15 years to 5 years ago has been just starting to get a bit of experience with what people might plausibly need when they want to shuffle around gigabytes or terabytes of data.
Yeah, it definitely gives a good amount of context for where you're ending up now with the Materialize project. So I'm wondering if you can describe a bit about what that is and some of the problems that you're aiming to solve by building it.
Yeah, no, that's perfect. So Materialize is in some ways sort of a natural extension of some of the research that we did, both back at Microsoft and also some stuff in between at various academic institutions, where we took what we learned when we were putting on our science hats about how to incrementally maintain computations that people had specified, which was great. We felt very smart when we did this, but it was something that wasn't super accessible to your average person who just wants to, in principle, wants to be able to type some SQL, press enter, see the result, and in principle, if they press up, enter over and over again, and ask the same question repeatedly, maybe that should be really fast. And I would say a lot of what Materialize is going after is a refinement of the experience, in some sense, of this underlying technology. We're borrowing very heavily from this work on incrementally maintaining computations, SQL-style computations, but others more broadly, and trying to refine it to the point that you can grab this Materialize binary and turn it on. It looks a lot like a standard database experience. You use something like pSQL to log into it, and you get to look at all sorts of relations there. You get to ask queries just like you would normally ask using just standard SQL constructs. And it just has some really nice performance properties if you ask the same questions over and over again. If you create views, create indices, you can start seeing results for what appear to be very complicated questions very quickly if we happen to be sitting on the appropriate data assets beforehand. So I would say the problem that we're trying to solve here, the lived experience is meant to be, it's a lot like a database that just happens to be fast when you re-ask questions that you've had before. And one of the problems that we're trying to solve is that a lot of the workflows for people using databases at the moment re-ask similar questions or similar classes of questions. So like a classic example, though not the only one, is dashboarding, where dashboards are repeatedly hitting your databases asking the same classes of questions over and over again. Show me stats on how many engagements did we have in the past many minutes, hours, whatever. The only thing that's limiting the freshness of that data is the database's ability to handle however many tens or hundreds of these queries that are repeatedly being asked about it from everyone's got a dashboard open. And if we can make that incredibly fast, then all these things can just be updating in real time. Like real time, like milliseconds, not real time, like minute by minute or something. So making a lot of these experiences more pleasant, ones where data are fresh down to the second and people's brains are thinking up new questions to ask second by second. Removing any speed bumps or roadblocks in either of those two dimensions. Either it takes a while for data to show up and actually get into the system, or possibly with some of the other frameworks out there, it takes a while for you to create to turn a new query that you have into an actual running computation. We're going to remove both of those and make some workloads immediately much, much better, and probably, my guess is, open the door for a lot of new classes of workloads that people wouldn't really have attempted before because they're just so painful. But that's a little bit speculative.
And in terms of how it fits into the overall life cycle and workflow of data, I'm wondering if you can just give an overview of maybe a typical architecture as to where the data is coming from, how it gets loaded into Materialize, and sort of where it sits on the axis of the sort of transactional workload where it's going into the database to the analytical workload where it's maybe in a data lake or a data warehouse or any of the other sort of surrounding ecosystem that it might tie into or feed the Materialize platform.
That's a great question. So there's definitely several different stories that you could go with here. And I'll start with probably I won't say the most simple one, but the one that's the most natural and least invasive or disruptive. One of the ways to think about what Materialize does, it's very much an analytic tool. Materialize itself is not, at first at least, planning on acting as a source of truth. So you have your database that's actually your transactional database that's holding on to all the information that you have about your sales or your customers or your products or whatever events are going on in your system. And what Materialize does is attaches to the output of that database. So your database typically is going to be producing, if it's MySQL, something like a bin log or some change data capture coming out of it. There are other tools, not ours, but other tools that will transform these different exhausts from the database into a more standard format, drop it into Kafka. So I'm thinking specifically of Debezium, if you're familiar with this. And if not, no worries. It's a thing that attaches to various databases and produces consistently shaped change logs that land in Kafka, and then we just pick things up out of Kafka. So we're decoupled from the transactional processor. You can think of us in some ways as a bolt-on analytics accelerator, something like that. We see what happens in your transactional database, and we give you fast read-only access to views over this data. So in some ways, we're like a read replica, or we behave a bit like one of those. It's not the actual protocol we're using at the moment, but you install something like Materialize just downstream from your source of truth. We don't really hope we don't interfere with the source of truth in any way. So that's roughly where it fits into this ecosystem. If you want to feed it with other sources of data, so if you've got Kafka streams that are being populated by not a database, maybe you have some IoT streams just sort of coming in of random measurements and observations that you've made. Probably with a little bit of tap dancing, it's easy to adjust these to something that we can consume. But we're very much at the moment looking at relational data models and the sorts of properties that they have, things like primary keys, foreign keys, the sorts of data flows that come out of SQL style queries. But yeah, does that roughly describe where it fits into the sorts of tools you're thinking of?
Yeah, so my understanding of it from your description here and also from the presentation that you gave at Data Council, which I'll link in the show notes, is that in some ways it can be thought of as a better use case for a read replica where you can get some actual improvements in the overall capabilities and characteristics of your workflow, as well as being able to incorporate additional data sources, as you mentioned, rather than it just being an exact copy of what's in your transactional system and being accessed in a way that's not going to impact it directly. So it seems like there are a lot of performance and capability gains, while at the same time sort of being able to access the same transactional records without it impacting your application that's actually feeding that data.
Right, that seems right. I mean, one way to think about it is that if you were going to build an analytic data processor, you wouldn't need to architect it the same way that you build a transactional data processor. So, of course, the people who are building transactional data processors they've been doing that for a long time. They've got a lot of expertise. But if the only thing you needed to do was support analytic queries or streaming, let's say streaming updates to analytic queries, you have the ability to use a totally different design. And indeed, this is data warehousing type tools have totally different designs from relational databases. And what we're doing, if you think of this as streaming data warehousing or something like this, analytic queries over continually changing data, we've picked a different architecture for how to do this than a traditional database would use, and just dropping it downstream of the traditional database lets us use this totally different architecture. It decouples the resources you might invest in the transactional side versus the analytics side, and lets you, Materialize is this scale up, scale out sort of solution where you can throw a bunch more resources at it if you have a large volume of queries, and you don't actually need to go and get a bigger database to be able to handle that. At the same time, it does some cool things that traditional data warehouses don't do with respect to frequency of updates and sort of this continual data monitoring stuff.
And so this is a good opportunity for us to dig a bit deeper into the overall system architecture and maybe talk about how you're able to handle these analytical workloads and ingest the data stream in a near real-time fashion for being able to continually update these queries.
Yeah, so Materialize has several components. So just like the high-level architecture, there's several different modules that you might not think of as part of the data processing plane. So I just want to call those out ahead of time. There's for sure components that mediate client access to the system, so things that handle SQL sessions coming in and make sure that everyone's got all of the right state stashed in the right places. This is control plane stuff. We'll get to the sort of the juicy data plane stuff in just a moment. Control plane, like people connect in, or people or tools connect in through SQL sessions. They have a little chat with the central coordinator for Materialize, and this is where we figure out which relations have which schemas. And if you want to see the columns on particular relations, all this data is sort of managed outside of the scalable data plane, so that we can do things like query planning and just the sort of more interactive, tell me about the structure of the data, the metadata interactively. But at that point, this coordinator, with the help of each of the users who have actual questions, assembles queries, these big sort of SQL queries that we're thinking of as probably going to be working on lots of data and subjected to continual changes in their inputs. It's going to take this, plan it out as a data flow. So if you're familiar at all with tools like, I would say, like things like Flink or Spark, these sort of big data tools that reimagine a lot of SQL style queries or data parallel queries as directed data flow graphs, where nodes represent computation and edges represent the movement of data. This is exactly the same sort of take that we're going to have. We're going to reimagine these queries as a data flow, which is great for streaming, because what we really want to do in these streaming settings is just sort of chill out while nothing's happening. If no inputs have changed, we just sort of hang out and as new changes arrive at various input collections, let's say, we want to prompt computation really only where we need to do work, right? So we'd love to be told, essentially by the movement of data itself, well, what operators, what bits of our query actually need to be updated. So if we've got a query that depends on 5 different relations, it's great to be told, well, this is the only one that's changed. Like your customer file is the only one that's changed. So push forward changes to this customer file and stop as soon as, if a customer changed their address, then that's not actually a field that's picked up by the query. We go quiet at that point and tell people the answers are correctly updated, nothing changed. So the coordinator is thinking through, how do I plan your query as a data flow computation? It gets deployed now to this data parallel backend that is where all of the work happens. These are where we have, let's say 32 concurrent workers or hundreds of concurrent workers. It turns out the numbers get to be a fair bit smaller with Materialize and timely data flow and stuff, because we've made some different architectural decisions from projects like Spark and Flink that allow us to move a fair bit faster. So we don't normally, at the moment at least, need thousands of cores. We can do the same sorts of work in tens of cores. But the data flow is partitioned now across each of these data parallel workers. They all share the same set of data flows. So think of the data flow as a map for the computation, like what needs to happen, when changes show up, where do we need to direct them to next. All of the workers share the same map. They all collaboratively do work for each of these operators. So we've got to join somewhere in here. Like there's just 2 streams of data coming in. We're supposed to join them together. The work associated with that join gets sliced up and sharded across all of our workers. So the join, if we have 32 workers, each worker performs roughly 1/32 of the join, or is responsible for the keys, 1/32 of the keys in that join. And I guess a really important architectural difference from prior work here is that each of the workers in this system is actually running its own little scheduler. Each of the workers is going to be able to handle each of the operators in the data flow graph. And rather than spinning up threads for each of these operators and letting the operating system itself figure out what gets done, we're actually, the timely data flow is bouncing around between operators at sub-microsecond timescales to perform this work. And this gives us a really big edge. Other bits of technology in this space, I would say, like scale out data parallel processing platforms, things like Spark and Flink, that partition away bits of data flow and don't allow them to share state. Basically, that's the main thing that's going on in Materialize that's exciting, is sharing of state between queries. Happy to dive into that, but I also just wanted to pause for a moment and make sure that I was still on target for the question that you had.
Yeah, no, that's definitely all useful. And as I was looking through, I noticed the timely data flow repository that you have, and noticed that it in the documentation, it mentions that it was based on your prior work on Naiad, which you mentioned. And I was also interested in the fact that you decided to implement it on top of Rust, where a lot of the existing and prior work for distributed computation, particularly in the data space, is based on either C and C++ or JVM languages. And so I'm curious what you found as far as the existing ecosystem in Rust for being able to implement things like timely data flow and some of the surrounding tools and libraries for being able to build something like Materialize, and the overall benefits that you've been able to realize from using Rust as your implementation language.
Yeah, no, that's a great question, actually. The historical explanation for using Rust isn't nearly as compelling a story as you might think. I was originally, so like 5 years ago, we were all at Microsoft, and Microsoft shut down the lab we were working at. And I was like, I should learn. At the time, everything we had written was in C#. So Naiad was all in C#. We were collectively thinking like, maybe we should learn a new language and sort of grow a little bit. I proudly announced to all of my coworkers I was going to go learn Go, and because they're very supportive people, they told me that was dumb. And in particular, there's like a cool blog post called "Go is not good" that I think is still relevant now. The author basically talks about like there are languages that are good programming languages. Not that Go is bad, but it lacks several good things that languages have been introducing. And they called out 2 languages they thought were good, which were Haskell and Rust. And that led me to pick up Rust instead. And these were early days. This is before Rust was 1.0. Things were still changing. And basically, I think I got pretty lucky. Rust worked out pretty well. In particular, I would say one of the main pain points that people have with Rust is this lifetime and borrowing system, which I think is great, but is really not that stressful in data processing frameworks. So in particular, all these data flow systems move the responsibility for data around between workers, at which point there's just not very much borrowing going on. So the main pain point for a lot of people using Rust doesn't manifest nearly as much as it might in a different domain. And the rails that Rust puts on everything to make sure that you don't screw things up have just been wonderful. There's a hilarious joke, but like one thing that I tell people is, timely data flow, differential data flow, all these things seem to work pretty well. They are actually used in production by some people. I don't actually know how to use GDB or LLDB debugger. It's just never come up. Rust has done a great job, from my experience, of removing the class of error, which is the pull your hair out, not understanding like, why is it even doing that thing? I didn't ask it to do that. So to my experience so far, Rust has been like 100% of the errors are just sitting there right in front of you in the code and are, you have bugs for sure, but they're delightfully debuggable, as opposed to like someone somewhere else in the code did a crazy thing which overwrote some of your memory and you just can't for the life of you figure stuff out. Right. So the flip side of that, the question I think you were actually asking was more about, given that Rust is such a new language and you'd love to just pull random support things off of the shelf, like adapters to different databases or support for Avro and JSON and stuff like that. Like what's there, what's missing. Yeah, there wasn't nearly as much stuff when folks are just starting up. You look at, is there a nice MySQL adapter? Oh, okay, there wasn't back then. There were a bunch of issues like this that have started to sort themselves out. And I would say that there's still some gaps, though at Materialize, at least, we haven't really run hard into any of these. Like we found stuff that we can use for each of these problems. And, I think in some cases people would love to just grab a thing off the shelf. So like an example, we rewrote some of our own query planning stuff because the query planning that we were familiar with, stuff like calcite, just isn't available in Rust. And if we were a Java shop, we would possibly just borrow that and have skipped thinking about some of these things, and that would be interesting. We would end up doing different sorts of things now. We wouldn't have spent as much time thinking about query planning, but instead we would hit our head with a lot of performance debugging. The anecdote I tell people from Naiad was that like getting the Naiad system up and running took, if I remember correctly, just like a few months. And from that point on, it was a year and a half of performance engineering working around the various vagaries of memory managed systems where they don't do exactly what you've asked of them. So it's, you end up doing different sorts of things. I think Rust has been great. Locally the people also think Rust is great, but of course obviously there's some selection bias going on here. People who are working at Materialize, in part, I think several of them did so because they're interested in Rust and making a swing at that.
And then in terms of the system architecture as it stands now, I'm curious how that compares to your initial design and how it's been updated as you have dug deeper into the problem space and started working with other people to vet your ideas and do some maybe alpha or beta testing, as the case may be.
Yeah, it's a good question. Let's see. There's been a few evolutions, so let me just mention a few of them. Not all of them are Materialize related. So pre-Materialize, you have things like timely differential data flow, which are essentially libraries that you can link against. You can write some Rust code, link against them, and you get a fairly performant outcome. I thought this was great. It worked wonderfully for me. I was totally fine with that. So I would say the main architectural change was in starting up Materialize and working with a bunch of people who came from real database backgrounds, understanding a different architecture that is going to require, not having compilation, for example, on the critical path. Figuring out how to design things so that when a person types a query and presses enter, the result flows as quickly as possible into execution without wandering through, let's say, 30 seconds of figuring out the right pile of code to drop down into a binary and run. Architecturally, like from that point on, I don't think. I mean, we've had minor architectural revisions where we've moved some of the responsibilities for certain bits of thinking between different modules that we have, and we've sort of broken things out into slightly more modules. But I don't feel that we've had substantial architectural revisions. We've had a lot of features that we weren't initially thinking would be crucial, and more people said like, yeah, okay, it's going to be important for you to not just pull data out of relational databases. People are also going to show up just with like plain text log files. Like, don't make sure that you understand exactly what you should do when someone points you at one of these. And like, oh crud, we got to go figure out how to do column extractors from plain text. And it's not fundamentally complicated, or lots of people have done these sorts of things before. We didn't need to change the architecture of the system, but we needed to be careful about exactly how we want to position it or what features we wanted the system to have. But I don't think there's been substantial architectural revisions that have gone on. It's still very much, there's what we think of as a fairly performant data processing plane and a coordinator control plane that drives this. And the exact words it uses to drive it have wibbled and wobbled a little bit. And exactly what the coordinator does in terms of showing people SQL has for sure changed at the same time. But there's not been any fundamental, I would say, re-architecting yet. And my guess is, based on the customers we're interacting, there's a lot of feature requests as opposed to fundamental redesigns in the near future, like in the sort of six month time frame. We have a list of just things to go and implement as opposed to things to fundamentally rethink. But at the same time, it's also sort of early days for us, so like it's not the right time to do a redesign anyhow. Like even if we were worried that something was not set up the way it should be, the right thing to do at the moment is to actually try it out on the domains that it works and see if we get traction there, as opposed to trying to be all things to all people.
And as you've mentioned a few times, the primary interface for Materialize is through SQL, and I know that you have made pains to ensure that you're fully compliant with the ANSI SQL standard for the SQL 92 variant. And I'm curious what the sort of edge cases or pain points were that you've had to deal with in being able to support all of that syntax, and possibly any extensions or built-in functions that you've added that fill the specific use case that Materialize is targeting.
Yeah, so there's a few, and they have different sorts of answers. So some things just require a bit more work. So yeah, SQL 92 has correlated subqueries is the thing that you can do, and correlated subqueries can have their own correlated subqueries. And this is especially painful in a data flow setting because you need to turn all of these subqueries into actual bits of data flow. Like a lot of databases they might think about building data flow to describe the course of execution or exactly where they should pull data from. But they can always, in some level, bail out if a query gets complicated and just do some nested loop joins that will just iterate through all of the whatever table you put together. So there's some nice escape hatches that exist in standard relational databases that we don't really have access to, because we actually do need to turn every silly query out there into something that we can run as data flow. The standard papers that you would read about decorrelated subqueries, so there's some from the early 2000s, they didn't cover all the cases. And we had to track down some more work that came out of Munich about how to decorrelate everything, not just the most appealing sorts of queries. So that's something where we just, we had to do more work. That's fine. I mean, it's good, it's good to understand. We learned a lot by doing this, and it's good to have learned that, because now we understand better what's easy, what's hard, what are the best, what can we discourage people from doing potentially. There's some other cases where things are just weird, like SQL has runtime exceptions, right? If you use a table valued expression, if you have a subquery that is supposed to only have one row in the result, you can ask, is my row equal to that row? And if that query actually has either 0 or multiple rows, it's supposed to be a runtime exception. And you would suspend query processing and return control back to the user. And that's not really a thing that we can do in this incremental data flow setting. Like, we can't really suspend execution. The data flow is supposed to keep running. If we suspend execution, we're killing the data flow. And that is disruptive. We have to think about what's the right way to communicate back to a person that they did something like divide by 0 or accessed an array out of bounds. And it's quite possible that we might change the spec here a little bit, that an array out of bounds is not an exception but is a null, is one thing. That's I think what Postgres does. Or if you divide by 0, maybe that should be a null rather than a runtime exception. And we will do the query processing. There's a query analysis ahead of time to try to confirm that your denominators might be non-zero, in which case we can confirm that they are, that this will never be null. But if you just might be dividing two random things that you produce as input, one by the other, we need to think of a thing that we can do that will not take down the data flow when you give us weird input. But at the same time, hopefully it doesn't totally confuse people who might have expected to see a runtime exception, have been using their database to do data validation. If you have a misparsed integer, what should we do? Yeah, good question. So those are some examples where we might have made a bit of a departure from the spec, just because the query processing idioms of SQL back in 1992 aren't the same as the view maintenance requirements that we have nowadays.
Yeah, it's definitely interesting to see all of the different ways that people will deal with SQL, because it's used so widely and so broadly, and there are so many different customizations that are necessary to fit a particular use case or edge cases that don't make sense for the original intent of where SQL was designed to run, because of the ways that we have expanded the space of data processing and data analytics.
So I think for the moment, we're definitely trying to do some things well and trying to find the customers. SQL 92 was quite a while ago. Trying to do those things well and seeing how far we get with that, as opposed to racing ahead and bolting on all of the newest extensions and features of, like we're looking at, for example, the moment of adding in JSON support, which we'll probably do because enough people are looking at it. But we very much want, I personally at least very much want us to end up being very good at specific sets of things that we understand, and we can tell people, if you want this, we do this very well, as opposed to having 27 different features that are all sort of half implemented and may or may not work in some corner cases. The local mantra is that we sort of want our README page explaining what Materialize can do for you to have no asterisks on it that say like, yeah, except actually this doesn't really work. A lot of other systems out there will say like, oh yeah, absolutely, you can join your data, but asterisk, like you can only use append-only streams, or like you need to make sure the partitioning is correct, or you have to understand what a table is versus a stream. Or we don't want any of those. So we want it to be dead simple to use for people whose problems fit in admittedly a restricted class of problems, and then grow out from there as we have confidence that we are providing an experience that is predictable and unsurprising and performant.
And then for people who are using Materialize, can you talk through what's involved in getting it set up and talk through some of the life cycle of the data as it flows from the source database or from the source data stream into Materialize, and how you manage the overall life cycle of the data there to ensure that you don't just expand the storage to essentially duplicate what's already in the source, and you're just making sure that you have what's necessary to perform the queries that you care about?
Right, great question. So what happens at the moment, and I should say that all this is sort of subject to change as we learn that people hate it or love it or want something slightly different. But the way the world works at the moment in Materialize is that we presume that you have some, like let's say MySQL or something, you have a well-accepted source of truth database, and at the same time, somewhere nearby you have, let's say, Kafka, a place to put streamy-ish data that is persisted and performant. There's a tool out there that we use and we sort of recommend people use at the moment called Debezium that attaches two various databases as essentially like a read replica, or reads the bin log, or it has a few different strategies based on the databases. And you turn this thing on, you point it at your database, and it starts emitting Kafka topics for each of the relations that you've named when you turned on Debezium. And the topics that it produces into Kafka basically contain before and after statements about various rows in various relations. So they say like, a change happened. A row used to be this before, now it is this afterwards, and a timestamp. And what we do, you turn on Materialize, and in Materialize you start typing things like create source from, and you announce the topic there. And when you announce a topic there, or a pattern for a class of topics, Materialize will go out, open up all these topics, start reading through each of them, and start pulling in these changes and presenting each of the topics now as a relation that you can query, and start mixing and mashing all of these different queries together. So this is roughly, this is a half answer to the question. I'm going to continue this one, but this is roughly what you need to do to get started with Materialize. You have a relational database that's holding onto your data. You transform it using a tool like Debezium into a changelog with a particular structure in Kafka, and then while using Materialize, you just point it at the Kafka topics and it'll start slurping in the data for you. In terms of how do you avoid being an entire replica of the entire database, and in particular the full history of all the changes for the database. So what you can do in Materialize is you obviously have the ability to select subsets of the relations that you want to bring in. You've got the ability, as you bring them in, to filter down the relations based either on predicates or projections, to filter down just to the data that you need. So if it turns out that you're only interested in analyzing customer data and sales data and only 5 of the columns from it, you're more than welcome to slice those things down. And Materialize has, through differential data flow on which it's built, some compaction technology internally that just makes sure that we're not using any more footprint than the size, the resident size of whatever relation you're sitting on. So although the history might go back days, weeks, whatever, we don't actually, unless you ask for it, we don't need to keep the days and weeks long history around, and we'll just give you query answers on now going forward. It's flexible though, like you could in principle say, please load the whole history and don't compact any of it, at which point we look a bit more like a temporal data processor. So we'll show you the full history of your query going back as far as we have history, basically up to history going back. But it is the case definitely that if you have, let's say, a few gigs of data that you're planning on analyzing interactively, we will have that few gigs of data live in memory. If your data is 10 terabytes, and you want to just do random access to it and play around with it, we're going to try to pull in 10 terabytes of data, and we might need to tell you about the clustered mode at that point, or try to give you some advice on thinning down the records a little bit so that you don't have quite so much of a footprint. But Materialize is going to manage all of its own data. It's not going to return to the core database and dump any of the analytical workload back onto it. So we're mirroring this stuff so that we can handle all of our workloads without either interfering with things upstream or without finding ourselves off-footed and not actually having the data we need indexed correctly. We'll see how that works. At the moment, this has been fine. Like a lot of the people we talked with, when they actually tell us, what do I need interactive access to? It's a surprisingly smaller volume of data than everything they've kept in their source of truth, or everything that they've ever dumped in their data lake. There's a much smaller hot set that they're interested in doing work over.
And as far as the scaling and storage of data within Materialize, you mentioned needing to keep the data in memory for being able to run these analyses. And I'm curious what the strategy is as far as spilling to disk for when you exceed the bounds of memory, and what the scaling strategies and scaling axes are for Materialize. And then in the process of describing that, maybe talk about where it falls in the CAP theorem.
Yeah, good question. With respect to the CAP theorem, it's sacrifices availability. That's easy. All of the timely data flow stuff, going back to sacrifice availability, they're all fail stop. So if something goes wrong, you lose access to some of the workers or something like that, we stop giving answers basically because we can no longer confirm that they're correct. That's where that lives. Materialize is definitely not. So CAP theorem is often applied to like geo-distributed systems that are likely to suffer partitions, and you have to say what are these trade-offs here. Naiad and timely data flow and Materialize are definitely, you can think of these more as living literally possibly in a single CPU to start with, like some large many core system or rack or something like that, but much more tightly coupled sorts of systems where if you've experienced a network partition, that's very surprising. It can happen, but this is why we choose to sacrifice availability rather than consistency. In terms of spilling, memory and spilling, all of the internal data structures are, although they're in memory, they're log-structured merge tree type things. There's a bunch of just big slabs of allocations, and the implementations just naturally, if you run it on an operating system that doesn't have an killer, it just pages out into virtual memory, and it's totally fine. One can manually drop each of these slabs of the log-structured merge tree onto disk and just memory map them back in. That's super easy too. If you rather that they literally be on disk and memory mapped in as opposed to in memory and then paged out. There's a bit of work that we still have to do and are planning on doing regarding Materialize's own persistence story, and it's almost certainly going to involve taking these slabs of log-structured merge tree stuff and shipping them off to S3 and bringing them back when appropriate. But yeah, there's not, unlike a lot of the JVM style systems that have big hash maps and shoot themselves in the head when they hit 64 gigs, these systems are super happy to just use the native mechanisms provided by the operating system. Performance doesn't seem to be impacted particularly.
And Materialize itself is a business, and the Materialize product is your at least initial offering. So I'm curious if you can talk through your motivations for forming a company around this and some of your overall business strategy.
Yeah, sure. So the motivation is super simple. I'm not going to source this correctly, but there's an expression of if you want to move quickly, you go by yourself, and if you want to go far, you go with friends. And Arjun, the co-founder, didn't use those exact words, but pointed out that while me hacking on timely data flow was super interesting, if we actually wanted to see if this had legs, could go anywhere, it was going to need to involve other people. So people to write various adapters, write documentation, exercise parts of the system that I had no idea how they're meant to work, the SQL compliance and stuff like that. And a company is the right mechanism to bring together a bunch of people, make sure that they get paid and are looked after, so that they can actually build something that's larger than just a research platform that's fun for writing blog posts and stuff like that. So part of the motivation of the company, there's a few different dimensions here, but part of the motivation was if you want to do something interesting with all of this work, timely data flow, differential data flow, whatnot, you need a framework to bring together some people, make sure that they get paid. And that's going to involve building a thing that other people might want and making sure that we get paid for doing it. There's other motivation too, like Arjun's motivation, I think is much more that this is absolutely an unmined area. So the work on Naiad and then timely data flow and differential data flow is great from his point of view, is great and undercapitalized upon. So why not try to actually take this and show people what it can do? And at the same time, make a lot of people in the enterprise infrastructure space really happy and collect paychecks from them just build something really cool and impressive. This is the motivation for the formation of the company, which isn't I haven't said anything about the business model yet, which is still my understanding is that enterprise tech has this very honest, healthy business model where companies that you're building technology for are relatively well funded, and if you actually do something valuable for them, they will pay you, and if you haven't done something particularly valuable for them, you probably won't get paid. So this is not nearly as bad as sort of consumer-facing technology where you have to hope to ride some zeitgeist of excitement. Now, like if you show up and you make a large Fortune 2000 company's life much bigger, much better, great, they're delighted, and we just need to make sure that we actually do that for enough people.
And the state of the product is currently pre-release, and you have a sign-up option on your landing page for being able to receive news. And I'm curious, what are some of the remaining steps that you have before you're ready to go with a general launch?
Yeah, so we're basically at the moment just spending it's like another month or two sending off some rough edges to make sure that. So the plan is absolutely to, in a few months' time, to throw this out there to make it publicly available. So people should be able to grab the source code, a binary, use it on their laptop just to try it out and see, do I like the look and feel of this sort of thing? Might I want to tell my boss that this is really cool and we should get some of this? And the steps, we have a roadmap for this in I think just about a few months, like in the 2-month time frame. And mostly what we're doing now are just making sure that these various known issues, like what is the look and feel of loading up CSV files from your file system as opposed to change logs from Kafka? Like, does that actually work properly, and are people delighted by how that works? And some other integration with some existing BI tools, for example. So if everyone had to just type raw SQL in, that's fine. A certain class of person likes that, but other classes of people like the look and feel of Tableau and Looker a bit more. And there's some open source BI tools that we're making sure that we're compatible with, so that people can point that at Materialize and get a bit more of an interactive query building experience rather than having to build their queries in some large text buffer and slot them in. So there's mostly some fit and finish types of issues like that. It's a sort of, the code is currently in a state that if we handed it to people, they could try it out. As long as they understood that it has warts, it'd be fine. And there's just a little bit of expectation management, basically. When we hand something out to people, if they go and try it and they realize that it doesn't exactly do what they need, well, we probably should have fixed that beforehand. So we're doing a bit of that in the next month or two.
Are there any other aspects of your work on Materialize or the underlying libraries or the overall space of being able to build a real-time analytics engine on streaming data that we didn't discuss yet that you'd like to cover before we close out the show?
There's lots of other really cool stuff for sure. I don't want to force any of it on people. Like, there's for sure a lot of thinking that one needs to go through and understanding. Just like the semantics of streaming data versus. So what Materialize does, for example, is incremental view maintenance. It takes a SQL query and it maintains it as your data change. That doesn't cover the full space of everything the person might possibly want to do with streaming data. So there's definitely a hurdle that I'm constantly anxious about is how many of the things that people actually want to do, of which there's unbounded numbers of things, actually look like incremental view maintenance of SQL. And in many cases, people have something totally different in mind, and you tell them like, if only you had said that slightly differently, it would just be a perfect fit for you. Is there any negotiation available here? So there's occasionally a bit of getting people to try to think through what they really need to see out of their streaming data. That's been pretty interesting and a big shift, that they're getting people to move from thinking about point in time queries to something that they're actually going to want to see change as time moves on is probably the hardest part. Getting other people to change their brains is really hard. Possibly not going to happen. We'll have to see. But that's one of the main things I'm most worried about in terms of are we gonna fit and click with a lot of people, is can we get them to understand the sorts of things that we're good at doing, and can they change their needs, basically? Do their needs line up with what we're capable of doing? We think so. We think there's enough people that are there, but this is a conversation that we have a lot with folks is, well, let me think for a second, just get my head around what it is that you actually do. I think that's probably going to continue to be the case for streaming SQL for a while, is what computers are actually able to do is pretty interesting. How do we wrap up in a language as pleasant as SQL an easy way to think about what do I want to have happen to my streaming data? As my data change, what do I want to have happen? But there's an unbounded amount of other stuff to talk about too. But let's let me throw that out as the main one that that I think about.
Well, for anybody who does want to get in touch with you and follow along with the work that you're doing and maybe have some follow-on conversations to the topics we discussed today, I'll have you add your preferred contact information to the show notes. And as a final question, I'm interested in getting your perspective on what you see as being the biggest gap in the tooling or technology that's available for data management today.
Oh, yeah, so that's tricky. So for sure, I have a biased take on this, but just based on what I've been doing for the past few years. I don't know, I would say that like a lot of what we've done in the past year at Materialize and before that has really been fighting with a lot of impedance mismatch between different tools and technology. So for example, we're using Kafka to get our data out and move it around, and Kafka just doesn't provide the right information about the state of the streams. And it's that's fine. You can work around that, but a lot of the tooling in tech and data management involves a lot of working around things. Even though in many of these cases we sort of know what the right answer is, just not everyone got on board with things at the right time. So like Hadoop took off in early days, for example, because it was so easy. And even when Hadoop took off, people already knew that this wasn't the right way to be doing things, but it was so fast out the door that people just piled onto it. And there's a lot of other tech that's like that. So for me, the thing that I always struggle with is the right way to figure out how to, if possible, roll back some of the early tech out the gate that missed important design elements and swap in things that once we figured out how to do things a bit better. But it's hard to do. Like it's hard to swap performance and sort of better architected tech in for things that missed some important things, but were still super valuable for people. And until, I don't know, I feel like if that were actually resolved in a pleasant way, one where there was a lot more off-the-shelf tooling that you could just take down and slot in for one class of tools. Like if all databases used the same protocol to talk to each other, had the same interpretation of SQL, our lives would be a lot easier. They don't, right? They all have crazy decisions that each of them made differently. Complying with all of them is, it just takes a lot of time when we could be doing more cool things. But I'm sure that's not the biggest issue that tech faces, but it's the one that, if you look at the dent on my forehead from what I've been hitting my head against, it has that shape.
All right. Well, thank you very much for taking the time today to join me and discuss the work that you've been doing with Materialize. It's definitely an interesting project and one that fits a need in between the sort of transactional engine and a lot of the analytical engines that we've got as far as being able to keep real-time information for people who are looking to do fast iterative queries or keep tabs on the current state of affairs of their data. So thank you for all of your work on that front, and I hope you enjoy the rest of your day.
Hey, thanks very much. I appreciate the time to talk, and all of the questions have been very thoughtful. I appreciate it.
Listening. Don't forget to check out our other show, podcast.init, at pythonpodcast.com to learn about the Python language, its community, and the innovative ways it is being used. And visit the site at dataengineeringpodcast.com to subscribe to the show, sign up for the mailing list, and read the show notes. If you've learned something or tried out a project from the show, then tell us about it. Email hosts at dataengineeringpodcast.com with your story. And to help other people find the show, please leave a review on iTunes and tell your friends and coworkers.